This optimization, and this is available on my website. If you go to this link, you should be able to get into this lecture and follow this. Okay, so it's a very complicated topic in the sense that it has huge ramifications in several other, areas of data analytics. And it's usually a graduate level course, right? It's usually a semester or two course. So I'll be giving a very brief overview of the subject. Okay, although I try to make it as useful as it can. Like I have constructed this lecture by taking the real data set and working through the examples of how optimization is done. Okay, so if you have followed it really well, you would be able to take this, everything, and then try to replicate on your data sets to produce some good insights about your data. Okay, so this is also a part of the other course that I'm offering on data science. So we'll be seeing several concepts here, different optimization techniques, and also some of the commonly used optimization techniques, and especially we will be looking into one of the applications in big data. And specifically, we would be focusing today on R. Okay, all the optimization packages and everything. The lecture will be built around R, and this fits into several areas. I mean, we can't really separate mathematical modeling and optimization. They go hand in hand. And all these image processing, all these machine learning and things like that, they are built around the core of optimization. Okay, so let's look into some of these concepts. One of the key concept is likelihood and maximum likelihood estimates. Have you heard about this? Have you done maximum likelihood? Yeah. So that's the first thing that we will see, and then we will be looking into cost functions. Okay, so cost functions are optimization functions, and we will be looking at one variable optimization, what it means to do an optimization in one variable through gradient descent algorithms, and we will look at a multivariable optimization. Okay, I'm going to give you an example of a multivariable optimization, and with a focus on introduction into big data optimization. How do they do a optimization on big data sets? And finally, we will be looking into local minima and convex functions. These are very important topics. I mean, the core of most of the optimization problems in general, or the functions that you will encounter in the real world, will be non-convex, which is a deep topic, which is a very difficult topic. And so we would not be looking into some of the aspects of nonlinear optimization, non-convex optimization, but only sketching through the convex optimization. Okay, so likelihood and maximum likelihood estimates. Likelihood is a probability, right? If you are given a data, you are seeing something, right? And the likelihood is a probability of observing a data given a model, right? So for instance, in just one variable case, let's say that you have some data, right? This is a x1, x2. This is a random variable in which you have these observations, and you can model with a parameter. Okay, so this is usually for the one parameter. Let's call it gamma, right? The likelihood function is defined like this: likelihood of gamma given this data is the probability of observing the data given the model. Okay, and if the observations are independent, right, there are some strong statistical assumptions behind likelihood. And if they are independent and identically distributed, independent in the sense that the outcome of one event doesn't affect the outcome of other, right? One observation doesn't like if you're throwing a dice, right, die, the outcome of appearance of number 2 doesn't affect the outcome of appearance of 3. So that those are independent events, and they have to be identically distributed, meaning they have to come from a same probability distribution. Then one can write this likelihood function as a product of the probabilities. Okay, once you have this, then you can do several things with this likelihood function. So let's look at a concrete example here. Okay, so Haynes is, if you have been in my other class, we extensively use this data set called the Haynes data set. It's a New York City's nutrition and health examination survey. Okay, so this is a huge data set. It's not a huge actually. It's about thousand observations where they collected people's various health status, their glucose levels, their hemoglobin levels, and all these blood related variables, urine related variables. And specifically, I think this was focused on trying to find out what's the prevalence of diabetes in the population. Okay, so for this data set, we will be working with this data set mainly. Okay, so what I'm doing here, how many of you know R here? Right, so good. So basically what I'm trying to do is I'm trying to import the data set, and I'm changing some of them as factors which are imported as numerical variables, and then trying to see if we have the data set here. So good data set. So it's all factors, and everything looks fine. And for instance, let's look at the gender variable, right? I can randomly sample 200 people and identify their gender. So that's what I'm doing here. I'm sampling gender from 200 people, and then I'm trying to just see the number of females in the population. So this is how my 200 sample looks like, and if I count, it's about 108 females in the population. Okay, so the first thing that we can do is that trying to estimate the number of population and the number of female in the population, the general population, from a random sample. So that's the idea behind likelihood, right? So the first thing we can do is we can assume that there are both proportions, right? So what is a likely, I mean, if you have to randomly draw some population, right? So what's the percentage, the proportion of females? And that is given by this parameter lambda here, okay? But there are only two categories here, male and a female, right? And each person is independent of the other. So this uh, perfectly fits in the assumptions of likelihood of function, right? So we can calculate the probability as a product of the probabilities by sampling each individual, right? So what is the probability of, so the probability is gamma if the observation is a female, otherwise it's 1 minus gamma if it's a male, right? It's a simple binomial distribution, right? So this is for 1 to 200, I can form this function, right? And then take the probabilities. So probability is a product of this likelihood functions, right? So once you have this, I can now evaluate the probability when men and women are equally distributed, right? So so female and male, we know that for a random sample they should be equally distributed, and so we can try to find in the likelihood of this probability, right? I can multiply all of them, and I have this huge number here. Okay, what about if the population, let's say that the men are overrepresented in the population by 80%? So in that case, the probability of females would be 0.2 and the men would be 0.8, 80%, right? And we can compute the probability, and we can see the likelihood of such an observation. The probability of observation when men are represented 80% is around it's extremely small, right? I mean, so we can generalize this as a function of a variable, right? As a function of a gamma variable, a parameter, and then graph the probability. So what I'm doing here is I'm taking the gamma as a parameter, and I'm supplying in the random gender here, and I'm computing the probability. If it is a female, I'm computing gamma, I'm taking the probability as, or if it's a male, it's 1 minus gamma, and then I'm taking the product of their probabilities and just plotting it, right? Once you do that, you have a distribution here. So this comes from the sample, from the observation, right? Now you can see that what's the probability of the females in the population when you observe 200 from the sample. So that's the general idea behind the likelihood, right? The same thing can be used, for instance, here, I'm trying to estimate the proportion of people with diabetes, like instead of males and females. I'm taking the diabetes population, and then I'm sampling 200 people randomly, and then trying to see what is a proportion of people with diabetes, and I have this. So for a different gamma, you will have a different probability likelihood, and you have this kind of a distribution, right? Or the likelihood function actually. So likelihood is not a probability. It's not a probability density, right? I mean, it is a function, but this function can be used to identify certain parameters underlying your observation, right? So that's called as a maximum likelihood estimate, right? The maximum likelihood estimate, it is what is the probability of looking, what is the likelihood of looking your data given some model. Here it's a simple binomial model. Gamma if somebody is a female, 1 minus gamma if somebody is a male. You can have complicated models too. But for these model, right, the maximum likelihood is the value of the parameters. You try to find gamma based on this curve. So that's the idea behind it, right? So mathematically what you can do is we can try to find the gamma by maximizing this likelihood function, right? So it can be simply evaluated using what is known as an optimized function in R. So I'm supplying lots of gammas here and I'm trying to compute the likelihood from this. So if you do that, we get around 0.54. It corresponds to this, it corresponds to this curve, right, where about 0.54 is the maximum it appears. So that's the likelihood of that's the proportion of females given this likelihood model that you have here, right? So similarly, we can do it for the diabetes population, right? I mean, it's the same binomial model. If somebody has a diabetes or somebody don't have a diabetes, right? So it's a simple binomial model, and the probability turns out it's about 0.75. Okay, so in our example, males and females, the maximum happens at 0.54, suggesting there are 54% of the female in the population, right? This is unlike the diabetes observation where the maximum is about 8%, right? I mean, it's skewed to the left of your graph, right? This is not far from the official estimate. The official estimate is about 9.3. I mean, you can get ballpark here and there depending on the random sample between I got about 11% and I got about 8%. So it varies, but then the official estimate is about 9.3. So this can be extremely useful tool to determine the underlying parameters of your model. The parameters meaning the mean here, right? I mean, if you're having this binomial distribution, the parameter is the probability of observing the number of females in the population or the number of people with diabetes, right? But then determining maximum likelihood can be difficult as the complexity of the models increase. So once you have the complex, so this is a very simple model, a male or a female, people with diabetes or people not with diabetes. You toss a coin, it's heads or tails. This can be modeled using the basic binomial distribution, right? You toss a coin, it's going to be either heads or tails. So the probability is P and 1 minus P. But let's say that if you introduce one more variable there, right? People with diabetes, people with not diabetes, and people would probably have diabetes but not diagnosed with diabetes. And that's one of the categories here. And how do you model in that case? So that goes into a complicated structure of modeling, statistical modeling based on what kind of a distribution. You can have a multinomial distribution and things like that, have a hypergeometric distribution. There are tons and tons of distributions that you can selecting a model is very, very important when framing questions and evaluating the answers. So that's why we need what is known as cost functions. At the end of the day, all these likelihood functions are evaluated using what are known as cost functions, right? Cost functions. What are cost functions? So cost functions, they map set of events into a number that mathematically represents the cost of some event occurring, right? It's usually it's denoted by the negative logarithm likelihood of negative log of likelihood, right? But why is this negative log? Have you seen this negative log in machine learning too, right? You have this entropy, right? Have you seen this negative log of negative log function? No. Okay, so it's okay. It's we have a good video here, but I thought the sound was not working. So let's go to the room PC and see this video. Hopefully, it should not be too loud. Let me see. It's a good video on why.
Imagine two machines. They both output messages from an alphabet of A, B, C, or D. Machine 1 generates each symbol randomly. They all occur 25% of the time. While machine 2 generates symbols according to the following probabilities. Now, which machine is producing more information? Claude Shannon cleverly rephrased the question. If you had to predict the next symbol from each machine, what is the minimum number of yes or no questions you would expect to ask? Let's look at machine 1. The most efficient way is to pose a question which divides the possibilities in half. For example, our first question, we could ask if it is any two symbols, such as, is it A or B? Since there is a 50% chance of A or B and a 50% chance of C or D. After getting the answer, we can eliminate half of the possibilities, and we will be left with two symbols, both equally likely. So we simply pick one, such as, is it A? And after this second question, we will have correctly identified the symbol. So we can say the uncertainty of machine 1 is 2 questions per symbol. Now, what about machine 2? As with machine 1, we could ask 2 questions to determine the next symbol. However, this time, the probability of each symbol is different, so we can ask our questions differently. Here, A has a 50% chance of occurring, and all other letters add to 50%. So we could start by asking, is it A? If it is A, we are done. Only one question in this case. Otherwise, we are left with 2 equal outcomes, D or B and C. So we could ask, is it D? If yes, we are done with 2 questions. Otherwise, we have to ask a third question to identify which of the last 2 symbols it is. On average, how many questions do you expect to ask to determine a symbol from machine 2? And this can be explained nicely with an analogy. Let's assume instead we want to build machine 1 and machine 2. And we can generate symbols by bouncing a disk off a peg into one of 2 equally likely directions. Based on which way it falls, we can generate a symbol. So with machine 1, we need to add a second level, or a second bounce, so that we have 2 bounces, which lead to 4 equally likely outcomes. And based on where the disk lands, we output A, B, C, or D. Now machine 2. In this case, the first bounce leads to either an A, which occurs 50% of the time, or else we lead to a second bounce, which then can either output a D, which occurs 25% of the time, or else it leads to a third bounce, which then leads to either B or C, 12.5% of the time. So now we just take a weighted average as follows. The expected number of bounces is the probability of symbol A times 1 bounce, plus the probability of B times 3 bounces, plus the probability of C times 3 bounces, plus the probability of D times 2 bounces, and this works out to 1.75 bounces. Now notice the connection between yes or no questions and fair bounces. The expected number of questions is equal to the expected number of bounces. So machine 1 requires 2 bounces to generate a symbol, while guessing an unknown symbol requires 2 questions. Machine 2 requires 1.75 bounces. We need to ask 1.75 questions on average. Meaning, if we need to guess 100 symbols from both machines, we can expect to ask 200 questions for machine 1 and 175 questions for machine 2. So this means that machine 2 is producing less information because there is less uncertainty or surprise about its output, and that's it. Claude Shannon calls this measure of average uncertainty entropy, and he uses the letter H to represent it. And the unit of entropy Shannon chooses is based on the uncertainty of a fair coin flip, and he calls this the bit, which is equivalent to a fair bounce. And we can arrive at the same result using our bounce analogy. Entropy, or H, is the summation for each symbol of the probability of that symbol times the number of bounces. Now, the difference is how do we express number of bounces in a more general way? And as we've seen, number of bounces depends how far down the tree we are. And we can simplify this by saying that the number of bounces equals the logarithm base 2 of the number of outcomes at that level. And the number of outcomes at a level is also based on the probability, where the number of outcomes at a level equals 1 divided by the probability of that outcome. Number of bounces actually equals the logarithm base 2 of 1 over the probability of that symbol, which gives us our final equation. Entropy, or H, is the summation for each symbol of the probability of that symbol times the logarithm base 2 of 1 over the probability of that symbol. And Shannon writes this slightly different, which just inverts the expression inside the logarithm, which causes us to add a negative, though both formulas give the same result. So let's summarize. Entropy is maximum when all outcomes are equally likely. Anytime you move away from equally likely outcomes or introduce predictability, the entropy must go down. Now, the fundamental idea is that if the entropy of an information source drops, that means we can ask fewer questions to guess the outcome. And thanks to Shannon, the bit, which is the unit of entropy, is adopted as our quantitative measure of information, or measure of surprise.
So yeah, so that explains why the cost function is logarithm. It's an entropy based idea, and also for doing certain mathematics, it becomes much easier if you choose logarithm over just working with a product of the probabilities, right? Because the logarithm function is additive than we are taking the product, right? There are other cost functions that are also used extensively in other areas of optimization, such as traveling salesman and stuff like that. But we would be focusing only on this type of a cost function for this lecture, right? So with this cost function as a negative log likelihood, we can formulate the cost of a given parameterization and plot it, right? So we can have this as a logarithm, and we immediately see that this is this the for the male and female example, we have this cost function, and the same thing that we can do it for the diabetes population, and you see that a different cost function, right? So these could be varying depending on the model, the data that you get, right? The maximum likelihood is the minimum of the cost function, right? Why is that? The value of the maximum likelihood, because it's a negative log likelihood, right? Log is also an increasing function, and negative log should be a decreasing function, right? And so you will have the maximum of the likelihood function is going to be the minimum of the cost function, and negative log function will also so that's why it decreases, and you will have that, right? Now so this is when we have to now do the optimization, simply because once you define the cost function, we can see that what cost does it take to optimize it, right? We now have a metric, right? So far we didn't have a metric. So yes.
The reason for the cost function because the minimum of the cost function is easy to find.
Yes. So we are minimizing the cost function to find the optimal value, the minimal value. That's going to be the maximum likelihood function for a maximum in case of maximum likelihood. Yeah. And there are ways to find this minima, right? So that's the whole idea of several optimization techniques, is to just find the minimum. The maximum problem can be cast into a minimum problem, so through the cost function, right? And so we are trying to find out the minima. Now, one of the simplest is the grid search. So what you do is, in grid search, it's an optimization technique in which we break the interval and evaluate the cost functions on each of those intervals, right? Then we can pick the value that gives the minimum. It's a very, very brute force. Remember algorithms class in which we discussed about the brute force algorithm. So it's a very naive algorithm, And it's called a grid search because it can be visualized like this, right? I mean, you have this, you break this grid, the gamma, into 10 parts or 20 parts or 1,000 parts, it doesn't matter. And then you can evaluate the cost function on each of that, right? And find the minimum. It's as simple as that, right? This is a very, very simplest algorithm. And this can be implemented as follows. You take the potential, the gammas, you divide it, and you apply for this function and try to find out the minimum, and then say that what's the minimum, right? I mean, it gives you a pretty accurate answer, actually, 0.075, right? This is what the diabetes example gave. It's about, right? I mean, it's a pretty accurate example, answer, right? But why is this approach bad? Before looking into that, why is the grid search approach is not bad? Well, it's bad.
We have to go through all the scenarios.
Right.
Computation.
Yes. So just for one, right? I mean, if there are several parameters, right? I mean, there even for a 3 parameter, you have to form a grid, and it also is restricted by the precision, right? So it depends on the parameters as well as how much of a precision that we want, right? So we can certainly do smarter by making use of the function itself. And that's the idea behind the gradient search algorithms, right? So for the gradient descent, right? So we slide along the function, right? It's like just seesaw, right? I mean, we just slide along the function and we've tried to find um, the direction that decreases the cost, right? So as you know, gradient of a function determines the direction, right? And the negative of the gradient is going to tell you the direction in which the cost function is decreasing, right? So it's mathematically, it's you can take the negative of the gradient, and with the parameter theta, this parameter is called a learning parameter, okay? So the learning rate, and we should also have a threshold for convergence because we are restricted by the precision, right? So we, once we have this, we can try to find out what's the minimum by going along the function of, of negative gradients, a decreasing gradient, right? And for a single variable, the gradient is extremely simple. It's the derivative with respect to the function, right? So in our case of diabetic population, right, we know what is a cost function. It is the log likelihood, and you can take the derivative of the function, which is 1 over the value of that. So you have this function, right? It's pretty easy, the cost function, right? The gradient of the cost function. So we can run this with this cost function. So you have an initial gamma, and you have a theta, and you have that learning parameter theta, and you have the tau, the precision, and you can write this cost function. You have um, I'm this is an analytical way of doing cost function, because we already know the cost function. I can easily take the derivative of it, right? And so you can and run this algorithm and plot it, right? So it's pretty easy. And the gradient descent also gives you the value of 0.075, right? Just as what the grid search gave. Actually, we can now look at the convergence. So we try to plot this, right? How the gradient descent looks. So it's the initial value here, 0.95. And the next value here, it jumps here, and then it comes here, and then it goes here, and then it converges to this value. And after that, the cost increases. So it stops with that, okay? So the gradient descent is a simple idea. It actually slides along the function and trying to in the direction of the minimum cost, right? And that minimum cost direction is chosen by the gradient. And so what one of the problems we might have is that we might not have an analytic form of the derivative. Most of the times the modeling becomes so difficult, and so you may not really have the concrete form of the derivative. In that case, you can do an approximation for the derivative, right? So if you know the elementary calculus, what's a derivative? It's a limit of the variable tending to the value, right? F of x plus delta x minus f of x by delta x. Remember? That's the same as this, right? I mean, you take the parameter, you add a small epsilon, subtract it, and then you divide it, right? I mean, it's so for this, we have this code here. Instead of the gradient, analytic form of the gradient, I can compute the gradient using this approximation. and then try to find the same. So beautiful. I mean, it also gives the same value, right? It's an approximation technique. All right, let's now go, that's a single variable, which is pretty easy. And let's go into the multivariable optimization, right? I mean, the idea is similar, just like single variable, the multivariable optimization is also similar, right? I mean, you take a gradient and along all directions, right? But in general, it's little more trickier. So let's take an example here. Okay, so in that Haynes data set, I had two variables. One variable is a hemoglobin variable, hemoglobin test, and the other is a glucose test. Okay, so they had two tests, and if a person has a fasting glucose levels of greater than 126 or the hemoglobin levels greater than or equal to 6.5, they are diagnosed diabetic. Okay, so this is the condition for classifying somebody as a diabetic. And let's say that if you want to estimate the probability of someone being diabetic, given these two variables, okay, so we can define the probability of someone being diabetic given A1C is greater than 6.5 is some variable that I have to determine. I want to find out based on these two variables what is the probability of somebody being diabetic given these two hemoglobin and the glucose levels. Okay, so that's the problem. So, and also defining the probability of somebody given diabetes, given the glucose is 126 is by this variable theta of glucose, right? Now, from the loss of probability, we can write this. If the hemoglobin is less than 6.5 and glucose, it's disappeared, but 126, it's P. If it is greater than, right, it's just the probability of a person is diabetic based on this hemoglobin alone, right? And if a person, if you're given just the glucose content greater than or equal to 126, but the hemoglobin is less than 6.5, the probability is just this, right? Otherwise, it's the union of probabilities. A person could be diabetic because his glucose levels are higher or his hemoglobin levels are higher, right? You can form this probability, right? And now, once you have this probability, we have to determine the variables theta, A1C, and glucose, right? I'm trying to frame it as an optimization problem here. Now you have to find out the variables theta, 1C, and glucose, and that determines the probability of someone being diabetic, right? And also we have the variable P that defines the population that is unexplained by the hidden variables, right? I mean, there could be some people who are diabetic, but they could have the hemoglobin levels lesser than 6.5 and their glucose is less than 126. So there could be some population which is not captured, right? So that can be directly computed from the observations. But there are some hidden variables, these two hidden variables that we need to find out. And this is what we will do, how to extract that information. Okay, so this is a code that I wrote to find it out. So what it means is that I'm trying to find out the hemoglobin contents greater than 6.5, glucose levels greater than 126 here, and also I know the diabetes status if they have diabetes, yes or no, right? And I'm only selecting that and I'm trying to look at the data. So it's like this: hemoglobin, if the person doesn't have, it's false, and also the diabetes is false. You have this such a big table. Okay, so they are about 1,000 of these values. Okay, once we have it, we can try to find out the variables that is not explained, the number of people who are diabetic, but that is not explained by both glucose and hemoglobin, right? So that can be done by just taking this, forming a matrix and trying to see. So if the diabetes is false, right, the 971 people have also glucose levels less than 126 and A1C levels less than 6.5, right? When the diabetes is true, there are 21 people who have glucose levels greater than 126 and A1C levels, sorry, less than 126 and A1C level less than 6.5. There are 21 people here, right? So what's the probability that is not explained by these two variables? Yes. So 21 divided by the population that has diabetes, right? So that's the 21 divided by 104, right? So that's this population that I'm calculating here. Okay. So now once we have that, we can now try to define the likelihood function. Okay. So in R, it's this is a function that you write to find the likelihood function. So what it says is that if the data, if the diabetes population is greater than 6.5, we have theta, the assign some value here, and if it is less than greater than 126, you have the theta glucose, like you have these two parameters, and then you can form the predicted diabetes here, just the function that we defined here, right? That's this function that we have defined here. So I'm just trying to frame this question in terms of the code here, right? So once you have that, we can look at the cost function, right? To see how far the cost function, how it varies, right? So you can look at immediately the cost function of these. For these probabilities, you can compute the cost function. So this is the cost of diabetes, and this is the probability of diabetes given A1C, the hemoglobin, and this is the probability given glucose levels, right? I mean, you have the more red it is, the lesser cost it is, right? Now, we see that the cost is minimized around this 0.6 and zero point 0.5, right? Now, this is, I'm trying to find out this value from optimization, and we hope our optimization techniques will give you this value, right? For multivariable optimization, it is same as that of a single variable. It's not too different. Here, the gradient function is given by a vector. For each of these, you have the vector of values. And in particular, in our case, we have, this is 2 dimensions, and your variables are restricted by A1C and glucose, and you have this. And just like in 2 dimensions, all this can be approximated by 1 dimension. So for the gradient, I'm adding this epsilon and then dividing by it. So I'm like trying to find out the gradient, right? I'm trying to find out the derivative here, and then you return this function. So this will help us to see how the gradient descent works in 2 dimensions, right? I mean, for the 2 dimensions, we can look at we can look into how it's going to work. So, for instance, if you start the point here, it's going to somewhere here and stuff like that. But essentially, it should converge here. If you are going to start from here, it has to go in this direction, or in this. If you start here, it will be in this direction, right? So this is a general idea of how gradient descent will work in 2 dimensions, okay? So we are now ready to see this gradient descent, and it's exactly the same as in 1 dimensions. We need to initialize conditional probabilities, and we will start with saying that my variables are 0.95%, right? I mean, so 95% will be diagnosed, and if I start with that, right, I can initialize the parameters 0.9, and then you define this alpha parameter, which is the learning rate, right, and also the tau. Now you set up the cost for this function, just like how we did the cost function, and then you update your gradient, right, and then we can plot it. So this is how the gradient descent performs. So it starts from here, it's going to converge going down, and then going to stop here, right? Just like how we did it in 1 dimensions, and we have these in 2 dimensions, except, and also we have the probability here. So the value of this, we can query that, and the value is about 0.62 and 0.48. Okay, so the probability of observing someone with diabetes given the hemoglobin value is 62%, right? And the probability of observing somebody with glucose is 49%. And for given both values, the probability is about 81%. Okay, so with this, we can say that it's best to use these 2 parameters than just using 1 parameter. Okay, so it's readily able to solve this question. You can have another variable too. I mean, it's the idea is the same, right? Instead of these 2 variables, you can have one more variable, and the logic and everything is going to be the same. So it's not going to be too different.
Sorry.
Yes.
The time in the
Mm-hmm.
that is to define how small the decrease is that you consider is good enough.
Yes, that's a precision, and I think if you're working with large values, the tau is not a learning parameter. The tau is the precision parameter. right? Usually precision of 10 to, I mean, it depends on the applications. Like if you're working with extremely sensitive experiments, then you may want to really, the tau has to be really, really small. Like for instance, let's say they are doing with this, quantum mechanics, quantum things like that, the large, hadron collider and stuff like that, where the precision is needs to be really small. It's huge, right? But in general, for practical purposes, about 10 to the negative 3, uh, 1 in 1000 should be a good value for approximation, right? So yeah, you can actually ask several questions and answer. I mean, just with this logic alone, you can ask several questions and answer them, right? There are several optimization techniques already implemented in R. I mean, this is, I just made this example for you to go through and see how the gradient descent works in action. But it's pretty easy actually. Once you set up the cost matrix, it's all you need to do is optim and then some initial value and then the cost matrix. It's going to spit out the optimization value. I mean, it's as simple as that. All the complication that I did, that you can, but then you can here you see it's 0.65 and 0.38. It's much a little bit different from what they had, kind of compares to a result, but it's different, right? I mean, this difference is because there could be multiple minimas, right? We will see that problem a little bit, okay? So, but in general, this optimum, right? I mean, it uses this function, right? This optim, not option, optim. There's a typo here. That actually uses Neldar made method. There is a method for finding the optimum, and so that method is a little bit better for quick convergence, but it's unstable. So there could be a problem with when there are more than one minimum, and there is another algorithm called BFGS algorithm, right? I mean, so there are lots of these optimization methods. There are tons of these. I mean, so one of them, it's if you can specify this BFGS method and it's going to use this method. The optim, check out this optim package. It's really cool. There are lots and lots of packages, and you have to honestly try different initial conditions. I'll tell you an example why we need to do that. Okay, so here it converges with 0.65 and 0.38. Okay, so and also it has methods. For instance, instead of using an analytic gradient, you can specify, if you already know an analytic form of gradient, you can use that gradient here by specifying gr equals and then specifying what gradient that you want to use, and it's going to give you the answer, right? And also, if we know how our values are going to be varying, right? You can specify that, and that could be an extremely important parameter for your analysis. It's called constraint optimization. It's a huge area in mathematics of how when you have a here we know that the probabilities cannot exceed zero point 0.9 and 0 and 1, right? So we know that, so we can specify how the optimization should use these limits to come up with good method for convergence, right? All right. Now, one of the key things, if you had noticed, right, one of the biggest problem with the optimization gradient descent that we saw is that at every time step, it has to compute the whole cost for optimization, and that could be a huge bottleneck. Like for instance, in Haynes, it's manageable. It's only 1,000 observations, but Mimic 3, it's one of the clinical databases. You have millions of data sets, data points there, observations there. Image, I think ImageNet has about 24 million images or something like that. It's crazy, right? I mean, so what would we do if we are working with all these formidable number of data or observations? In that case, what we can do, what is known as a stochastic gradient descent. Okay, so the idea is simple actually. If you look at the cost of error for one observation, right, doesn't affect the other observation because they are independent. One patient is independent from the other patient. So the cost is independent, right? So we can randomly choose some observation to get an approximate estimate. So that's the idea. Don't find the cost by sampling, adding everything. but just randomly sample. The random sampling is very important there, okay, because of mathematical reasons. So if you randomly sample, you can have a good approximation for the cost, right? So once we have an approximation for the cost, we can do that. So that's the idea. So for instance, here I chose 1,100 observations at each time step to estimate the cost of glucose levels and A1C levels. I have this observation, and what we do here is there is an iterative parameter for every iteration. I choose some random observation, random number of observations, right? It's only 100 points here, and calculating the cost, and it beautifully converges to the value that we have here, right? I mean, it's closest to what we found out by multiple variable gradient descent. In fact, we can plot it with different colors. So it was like purple for the first iteration, yellow for the second, and blue for the third, and we see that it is really converging in 3 iterations by randomly choosing the number of people, right? I mean, it's so imagine how much it could save if you have like millions and billions of data points. By random sampling, we can like cut down the cost like anything using the stochastic gradient method, right? So for instance, in our example, it's established that A1C is like 6.5 or 126 for the glucose level, right? What will you do if you don't know this? If you don't know these values, one of the ideas that we can do is we can actually take these pairs of values, right, and we can compute on several nodes, right? So instead of just doing everything on one machine, we can parallelize, right, and we can use a map reduce framework or high performance computing, and the stochastic gradient descent can be used in every we can randomly take some pairs and then distribute it across, right? And so and we can choose the minimum of the minimums, and that will help us to decide the numbers that are good, right? So it can also work backwards. Just instead of knowing that, okay, A is the hemoglobin levels has to be 6.5, and the glucose levels has to be 126, we can do it backwards, like trying to iterate through by giving it to a different clusters, right? So this is the power of this analysis. Okay, so it can try to find out by uh, the best variables in your data, right? All right. So for the cost function is all good. We had one minima, we had very simple cost functions, but consider this function. Okay, so I just made up this function, right? And we are trying to find the minimum through gradient descent. Fine, great. I'm doing this function theta, theta plus 1, etc. And I'm taking the gradient, fine. And I'm starting with the initial parameter of minus 2.5, right? And I'm trying to run down this gradient descent, and it gives minus 1.29. Okay, great, it's fine. Let's look at the function here. Is it good? I got minus 1.29 as a minimum. What's the problem here? It's not the minimum, right? So this is a huge problem. And the thing is, because we have two types of minimum, one is a global minimum and local minimum. Okay, one of the very toughest problems in optimization comes from having multiple minimas. Okay, so that is why it is sensitive to initial condition. If you start with the initial condition here, right, it's going to converge to this minimum. If you start with the initial condition here, it's going to converge to this minimum. Okay, it also depends on how your learning parameter is. If you are having a too big of a learning parameter, it may pass the minimum and go in here, right? I mean, so there are all sorts of things. I mean, it's highly. That's why it's important to try several initial conditions. We don't know how the function looks like in multi-dimensional spaces. You know, it's going to be crazy. Can only, if this is 2 dimensions, it's easy to look at it at least. If you have 3 variables, it's going to be 3 dimensions. If you have 10 variables, if you have gene expression data, 20,000 variables, I mean, you don't know how the space is going to look like. So how will you go and try about doing this? It's one of the things is to give several initial condition and hoping that we have converged on a global minimum. right? So gradient descent doesn't give claims to giving global minimum, right? So it could be optimal or suboptimal, right? So are we out of luck? Is this the only hope that we can have? Not really, actually. There are some classes of functions, right? I mean, now in those classes of functions, the local minimum and global minimum coincide. Okay, those functions are called convex functions, and the whole field is called convex optimization. The field of subfield of convex functions, how we are going to do the optimization is called convex optimization. So loosely speaking, a function is convex if every line segment that you draw, the function lies above the line lies above the function, right? So let me show an example here. Here you have this function, right? The problem is that when you draw these two line segment, right, the function lies above this line segment, and that's this is a non-convex function, right? For a non-convex function, this kind of a thing happens, but for a convex function, the graph should always lie below these two, so they can't have any global multiple. I mean, they can't have any two maximums, right? So for all convex functions, you can take it for granted that if you have a convex function, you are nice. I mean, you're good to go. You don't have to be worrying about all these kinds of headaches and multiple minima, because it's going to, the global minima is going to coincide with the local minima. Okay, and there's a simple mathematical proof. Okay, I thought I should end with a good mathematical proof, but it's not too complicated. So mathematically, convex functions are defined by this. So what this means is that a line segment joining 2 points y and x, right, lambda y times 1 minus lambda is always, right, lesser than this, right? This is the line segment joining f of x and f of y. So if you have this, the function, right, the function always lies uh, lower than the line segment joining that, right? Now once you have that, there is a simple proof that you can say, suppose that f is a convex function, then the local minimum is also a global minimum, and let's say that it's not, right? By simple mathematics, you can see that the function, right, f of x plus this, the function should lie between this f of, by the definition of convexity, right? But f of y by assumption is less than f of x, so this value is going to be lesser than f of x, right? Do you see that? Because this is f of x, this is a negative number, and this is going to be less than f of x. So there is a small there's a small ball around x such that f of z should be less than f of x. Therefore, x is not a global minimum. So this is a contradiction, proof by contradiction. I mean, forget the proof, but at the end of the day, take it that if you have convex functions, the world is much nicer and you will be able to get minimum. Okay, probably you may have to try there. Still, it might be sensitive to learning parameters and stuff like that, but some of things can be reduced. But several of the problems of global optimization is like one of the biggest outstanding problems. I mean, it's so those are some of the things that are that are difficult. I mean, it's just to give you an exposure of some of these things. I mean, even with this lecture, you should be able to take your data set and trying to find probabilities using that. Just change the data set and the values, and you should be able to do it, right? Trying to find the optimum optimization. I mean, and trying to find the probability and stuff like that. So yeah, I think we will stop. And there is an excellent tutorial. Go in here. It's almost some of these things are just this is MIT's brain. Almost all the worked out examples I worked out from a particular data set, but they have it for a general data set. Some of them, I think they had a general data set, but I focused on biomedical informatics. So, if you want, you could take it as a good project. Actually, have a data set, you can try to optimize on the various variables and try to find which is good, gives the maximizes the probability. All right. So yeah, let me stop here, and if you have questions, I'll be happy to take it. Let's